We just drew Lewis dot structures for all of these, so let's keep going now. And we're going to now write Lewis structures for a molecule with one central atom and no octet rule exceptions. The octet rule exceptions get tricky. Some atoms will have an expanded octet. Some won't need to fill an octet, so that's when we get into these exceptions. So Lewis structures or Lewis dot structures, same thing. Let's go through what drawing these is going to look like. To draw Lewis dot structures, first we want to draw the skeletal structure of the compound showing what atoms are bonded to each other. We want to put the least electronegative element in the center. Electronegativity increases going left to right, and it increases going up a group. The least electronegative elements then will be something towards the left or something further down on the periodic table. Next, we want to count the total number of valence electrons. If we have an anion, we need to add 1 electron for each charge. For instance, 2 minus charge, that would be an additional 2 electrons. A plus 1 charge, on the other hand, we would be subtracting an electron. So we need to watch out if they're a non-neutral molecule or compound or ion, then we'll either need to add electrons if it's a negative charge or take electrons away if we see a positive charge. That's because electrons themselves are negatively charged. Additional electrons will cause a neutral atom to then gain that negative charge, like we know for anions. Then we're going to try to make every atom happy and have a happy complete octet, except for atoms like hydrogen that want to fill a duet instead. For the most part, we'll be thinking that all the other atoms want to fill their octet. And here's a nice description on the octet rule. So for most common molecules, the best chemical bonding arrangement is that in which each hydrogen atom is surrounded by 1 pair of valence electrons, and each atom that's not hydrogen is surrounded by 4 pairs of valence electrons. 4 pairs of valence electrons, that can be either in the form of a bond or in the form of a lone pair of electrons. This is a pair of electrons within that bond, right? Each bond holds 2 electrons. Then this lone pair of electrons is also then, of course, a pair of electrons or 2 electrons. Then fourth, if the structure contains too many electrons, form a double and triple bond on the central atom as needed. So we'll practice doing that. We'll see what happens as we start to draw these structures. Let's go for it now. So let's draw the Lewis dot structure for N3- or an azide ion. For this ion we're going to draw, that is 3 different nitrogen atoms with a -1 charge. Those are all the same atom, but when we're asked to draw Lewis structures of a molecule with more than 2 kinds of atoms, we must put some thought into how the atoms are arranged. There's generally a lot of different possibilities for how those atoms are arranged, but we can think about some helpful tricks. So for molecules with 5 or fewer atoms, one of the most useful tricks is to find the atom that needs to be at the center of the molecule. We'll go through those tips on the next slide, just looking at these structures here, for example. This is composed of 3 atoms, so 2 H's and an O. We recognize H2O as water. Oxygen here is in the center of the atom rather than a hydrogen atom. So if we were given this formula of H2O, we'd see that oxygen would need to go in the middle. And we'll talk about why we think that would be in the middle. Carbon dioxide, 3 atoms, C and O2. Given this formula, we're deciding now that carbon goes in the middle. Can you start to see a pattern for which one of the atoms we put in the middle? It's not always oxygen, right? Because here it's in the middle, but here it's on the end. One thing you may be noticing for what goes in the middle is it's the unique element. It's the unique atom. We have two H's, but just one O. The O goes in the middle. We have two O's, but just one C. The carbon, the C, goes in the middle. With this one now, CH2O, there's two hydrogens, so that's not unique, but there is only one carbon and one oxygen. How do we decide between carbon and oxygen which one goes in the middle? Well, something here that we read is that we should put the least electronegative element in the center. Is carbon less electronegative than oxygen? Well, yes, it's further to the left. So carbon is less electronegative than oxygen. Carbon goes in the middle for this molecule. There's some additional tips as well for finding the central atom of a small molecule. Number one is since atoms of hydrogen and fluorine can only form one bond, they are never the center atom. Hydrogen has one valence electron itself. It only needs to form a bond with one other atom. It's not going to be in the center because it only wants to form that one bond. Fluorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. With 7 valence electrons already for this halogen, fluorine only needs to form a bond with one other atom. Fluorine doesn't want to form a bond on the other side of its atom. It just wants to form one bond. So fluorine's not going to be in the middle. It's going to be on the end and just be bonded to one other atom to fill its octet. Rule number 2, since atoms of carbon form 4 bonds, carbon is often the central atom. Carbon has 4 valence electrons. It likes to form bonds to 4 other atoms to fill its octet. So clearly it's an atom that could definitely be in the center because it can form 4 bonds like this. Third is what we've seen. So atoms of highly electronegative elements tend to prefer lone pairs over bonding pairs. These are lone pairs. This is a bonding pair. So the more electronegative elements prefer to have lone pairs around them rather than bonding pairs. So the highly electronegative elements don't like to be in the center either. This means the least electronegative atom in a molecule often tends to be the central atom. So the less electronegative atom typically in the center. Here's another set of similar guidelines as well. So as mentioned, the element that appears the fewest number of times, or it's the unique element, tends to be in the center. Carbon is commonly in the center as well. Then again, the least electronegative atom goes in the center. The least electronegative would be the one that's further to the left because electronegativity increases going left to right. Or it'd be the one furthest down because electronegativity increases going up a group. If we can know the central atom, that helps a lot in figuring out the Lewis dot structures. Now for the example we have, so this azide anion, we don't need to worry about which one we put in the middle because all these nitrogens are the same. So in step number 1, we would be figuring out what we put in the middle and then draw this sort of skeleton figure for now. To draw this first step, it's totally fine to draw it in the pairs of electrons like this as we're getting used to figuring out what is actually in a bond. As we start to get more familiar though, what's in a bond is one pair of electrons. every bond has 2 electrons. It's just harder to see or think about it like this, so we could draw it like this, where this is clearly a pair of electrons or 2 electrons between each nitrogen atom. Once we start to get comfortable with this, we can also draw the skeleton like this. So nitrogen, nitrogen, nitrogen with 1 bond between each atom for now. Again, this is just drawing out the quote skeleton of the structure. The skeleton of the structure will show 1 bond between the central atom and the other atoms around it. So next now would be counting the total number of valence electrons, and we need to be sure to account for, is it an anion or a cation or neither? So N3 with a minus charge, each nitrogen has 5 valence electrons based on nitrogen's placement in the periodic table. So this is 5 valence electrons times 3, that's 15 valence electrons, but we haven't yet dealt with this negative charge here. Because we have a negative charge, we need to add on 1 additional electron to this total. That means in total for this ion, we have 16 valence electrons to work with. This was our skeleton drawing so far. How many electrons have we used up from just drawing this skeleton? Well, it's 2 electrons in each one of these bonds. So minus 2 electrons for one bond and minus 2 electrons for another. 16 minus 4, that means we have 12 electrons remaining. Essentially what we're doing is figuring out how many valence electrons we have to work with, and then we're placing them around the atoms to have them reach a happy octet ideally. We have 12 electrons left at this point because again we had 16 by counting these up. 5 valence electrons per nitrogen times 3 is 15. Then with that negative sign there means we've added on another electron, so that's 16 electrons total. We used up 1, 2, 3, 4, so we have 12 remaining at this point after we've drawn the skeleton. Now we need to add any remaining electrons as lone pairs around the atoms. If we have a choice on which atom to add those lone pairs of electrons to, we should add the lone pairs to the more electronegative atoms first. These are all the same, they're all the same electronegativity, so it doesn't matter where we start to add on those electrons. But as we're adding on those electrons, we should be careful not to exceed the octet rule. This is already 1, 2, then 3, 4, 5, 6, 7, 8. So technically this one has a happy octet, this one nitrogen on the end. 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. We just used up 6 here, so now we have 6 remaining. At this point, we're kind of figuring out what may work by doing some trial and error. So now 6 more to use up. We shouldn't put them on the middle nitrogen because that already has 1, 2, 3, 4. We could, but that would end up with 5, 6, 7, 8. When we're starting to add on electrons like this, the best option is to add them to the atoms on the side. The atoms on these sides are the ones that have the greater electronegativity. Here, they're all the same electronegativity, but as we start to see other kinds of molecules that we're drawing, we should get used to adding lone pairs to the more electronegative atoms, which from what we know are going to be the non-central atoms. These would be the more electronegative because we put the least electronegative one in the middle. So we have 6 left. Let's add it to the side atom. We added 1, 2, 3, 4, 5, 6. Now we have used up all 16 electrons. We're not yet done. We're just figuring out what might work. We definitely need to check the octet rule, and we can already tell the nitrogen in the middle doesn't have a happy octet. At this point, the nitrogen in the middle has 1, 2, 3, 4 electrons around it. It needs 4 more. So we kind of work through number 3, except that middle nitrogen atom does not yet have a happy octet. To make this work, we need to go on to step 4, where we start to think about the double and triple bonds. If we change some of the single bonds to double or triple bonds, that could help the central nitrogen reach a happy octet. And so because the octet rule is not yet satisfied, we need to convert some neighboring lone pairs into bonding pairs, also thought of as bonds around the atoms that are lacking that complete octet. So right now we're looking at this structure. We need to sort of play around with this and see if we can pull this lone pair of electrons into this bond to then form a double bond. If there is more than one way to satisfy the octet rule by adding on double or triple bonds, that could mean taking this lone pair into here, maybe even taking another lone pair into here to form a triple bond. It's clear there are a few different options we could work with to achieve a happy octet for all 3 nitrogen atoms. To pick the best Lewis structure, if we have a few different options, we need to pick the Lewis structure with the smallest formal charges. We have not yet talked about formal charge. That's the next topic we'll go through. Because this molecule is symmetric, it sort of limits how we might do this. How I would approach this is I see the central nitrogen only has 4 valence electrons at this point. So I'd practice taking 1 lone pair here and 1 lone pair here. Now that lone pair of electrons becomes a double bond and a double bond. That leaves 2 lone pairs here and 2 lone pairs here. Does this nitrogen have a happy octet? Let's see. 1, 2, 3, 4, 5, 6, 7, 8. So yes, this one is all set. Then the central nitrogen, 1, 2, 3, 4, 5, 6, 7, 8. This nitrogen on the right, because it's symmetric, it will look like this one. So 1, 2, 3, 4, 5, 6, 7, 8. So this structure is definitely a viable option. Right now I just took 1 lone pair from this nitrogen and 1 lone pair from this nitrogen and formed 2 double bonds around the central nitrogen. We're not quite done in thinking about the possibilities though. Because what if I took 1 lone pair here and then a second one from this nitrogen? Again, because this is symmetric, if I do it with this nitrogen, it would look the same if I did it with this nitrogen. If I took 2 lone pairs from this one, it would look the same as taking 2 lone pairs from the one on the left. That means this one on the right is currently unchanged. I could have done this to the one on the left instead, and left this one unchanged, but taken 2 lone pairs from here. But again, it's symmetric. I ended up taking 2 lone pairs from this one. That leaves 1 lone pair and then a bond here and a bond here from this lone pair and this lone pair. This is an interesting option as well as this. Which one is better does come back to a formal charge. We want to minimize the formal charges, and we'll go into that way more on the next topic. Before saying definitely with certainty that this is a viable structure, I needed to check the octet rule. 1, 2, 3, 4, 5, 6, 7, 8 for this nitrogen. 1, 2, 3, 4, 5, 6, 7, 8 for this one. Then 1, 2, 3, 4, 5, 6, 7, 8 for this one. So these both satisfy the octet rule, so therefore they are both viable options. If one of them did not satisfy the octet rule, that's probably not the best option. Let's see how we would use formal charges to pick which one is better. To assign formal charges, again, we're going to go through this a lot more on the next topic. I'm going to tell you this way I think about it. Nitrogen has 5 valence electrons. It wants 5, quote, things around it. If it has an extra thing around it, it has a -1 charge. So stay with me here. Let me show you. So 5 things around it from the 5 valence electrons, 5 things being 5 regions of electron density. This nitrogen in the middle has 1, 2, 3, 4, 5 things around it, 5 regions of electron density. This nitrogen's formal charge is 0. This nitrogen has 1, 2, 3, 4 regions of electron density around it. It wants to have 5. So it wants to have 5 regions of electron density because of its 5 valence electrons. It actually has 4 regions of electron density around it in this version of the structure. So it has 4 regions of electron density around it. 5 minus 4 gives this nitrogen a +1 charge. Let's try it with this one. So we have 1, 2, 3, 4, 5, 6, 7. For the, quote, regions of electron density, or the, quote, things around that atom, each lone electron counts as 1 thing. And thing is not a great way to say it, it's just for a lack of a better term here. So each lone electron results in 1 thing. Each bond coming from that atom also results in just 1 thing. So 1 because of the bond, 2, 3, 4, 5, 6, 7. So again for this one, it wants 5 because the 5 valence electrons. It has 7. 5 minus 7 is -2. The formal charge on nitrogen in this conformation is -2. So 0 + 1 and -2. Before pressing play, try to figure out the formal charges on each nitrogen in this structure. So let's try this one on the left. It has 1, 2, 3, 4, 5, 6 things around it. It wants 5, but it has 6. That means the formal charge on this nitrogen is -1. The central one has 1, 2, 3, 4 things around it. It wants 5, but it has 4. Its formal charge then is +1. The nitrogen on the end here is the same as this one, 1, 2, 3, 4, 5, 6. It wants 5 from its 5 valence electrons, but it has 6, so -1. So -1, +1, and -1, those are the formal charges on this structure. Now, in figuring out which structure is better, we want to have the minimum lower formal charges. We want the formal charges to be the lowest possible. The best formal charge is when each atom has a formal charge of just 0. When that's not possible, we pick a structure that has the minimum formal charges. So 0, +1, and -2. This -2 is worse. It's a worse formal charge than -1, +1, and -1. So the structure that wins out here is the one without -2, just +1 and -1. That's better than -2 and +1. So this is not ideal. +1 and -1 are more ideal. This is the better structure for that ion. So here's our final Lewis dot structure seen here as well. Because this is an ion, we also need to include these brackets here. So for ions, we need to include the brackets and then show the charge on the ion outside of those brackets. So because this molecule is a polyatomic ion, we don't really draw Lewis dot structures for non-polyatomic ions. So for polyatomic ions, we place those brackets around the structure and we write its charge in the upper right corner outside of the bracket. So here's the structure, here are the brackets, here's the charge. There are lots more practice problems on Lewis dot structures. If you want to talk through any of them or go through any practice problems together, definitely let me know. The more practice you get, the more comfortable you'll get in drawing Lewis dot structures. And so next, let's go into calculating formal charges. Instead of using that thing method, we'll go through a different way to think about formal charge. If the thing method works for you, then that's definitely okay to think about it. But let's go through this topic formally now. And so here's another hint at the -2 formal charge being extremely non-ideal. We want to avoid formal charges of -2 in our Lewis dot structures. The formal charges we would want are +1, -1, and then the best formal charge is just a formal charge of 0. -2 is definitely not an ideal formal charge. So let's take a closer look here at formal charge. What the formal charge is, it's the difference between the number of valence electrons in an isolated atom and the number of electrons assigned to that atom in a Lewis dot structure. To calculate the formal charge formally with an equation, we can look at the total number of valence electrons in a free atom, or in that free atom. For nitrogen, we knew that was 5 valence electrons. This is minus the total number of non-bonding electrons, or in other words, the electrons that are in lone pairs, but the total number, where a lone pair then counts as 2 electrons here, minus then 1/2 times the total number of bonding electrons. So the electrons in a bond is 2, but we do 1/2 times 2. So for every bond, that would be a value here of just 1. When drawing Lewis dot structures, we need the sum of the formal charges of each of the atoms in that molecule or ion to equal the charge on the molecule or ion. Let's see if that worked out for the structure we selected. Overall, this is a -1 charge like we see here. We picked this Lewis dot structure. That means -1 plus +1 plus -1. -1 plus 1 is 0, -1, that totals up to -1. So as expected, the formal charges on each of these atoms does total up to -1 overall. So that needs to be true for all of our formal charges, for all of our Lewis dot structures that have a charge on them. If the overall ion is +1, then all the formal charges on each of those individual atoms, that needs to sum up to also +1. So let's look at these two different structures of formaldehyde, or CH2O. Using the formal equation for formal charge, let's figure out what's the better of the two structures. So the total number of valence electrons for hydrogen, that's 1. Carbon, that's 4. Oxygen, that's 6. So again, it's going to be important to be able to look at the periodic table and say how many valence electrons for each of the atoms we'll see. We're focused mostly on the S and P block atoms of the periodic table. And there's a double bond here as well in this structure. So let's compare these two. And the structure we're comparing here actually has a lone pair on the carbon, a double bond here, and then a lone pair on oxygen. So based on this structure, so going through this one first, here's our formula. The number of valence electrons in the free atom for carbon, that's 4. So 4 valence electrons for carbon. How many non-bonding electrons? 1, 2. So we're subtracting the non-bonding electrons. How many total number of bonding electrons? Well, 1, 2, 3, 4, 5, 6. So we take 1/2 times 6. 4 minus 2 is 2, minus 3 here is -1. Now for oxygen, the total number of valence electrons on oxygen on its own is 6 valence electrons. It's in group 6A. Total number of non-bonding electrons, 1, 2. Number of bonding electrons, 1, 2, 3, 4. Let me erase this so I can show it for oxygen. 1, 2, 3, 4, 5, 6. So 1/2 again times 6. 6 minus 2 is 4, minus 3, now that's +1 for oxygen. Let's try this for hydrogen just for fun and just for practice. The number of valence electrons in a free atom of hydrogen is 1. Non-bonding electrons, well, none, there's no lone pairs. Minus 1/2 times the total number of bonding electrons, so 1, 2. 1 minus 0 minus 1. The formal charge on these two hydrogens is 0 because they're symmetric. They both have one bond coming from their atom. So 0 formal charge for both hydrogens. Carbon -1, oxygen +1. Those are pretty okay formal charges. They're not -2, they're not +2. They're in an acceptable range for formal charges to be ideally 0, but if they have to be something other than 0, +1 and -1 are okay. For this structure, hydrogen also has one bond coming from it, so for both of those hydrogens, the formal charge is again 0. Now for carbon, the number of valence electrons does not change. How many non-bonding electrons here? Well, 0. They're all in bonds coming from carbon. The total number of bonding electrons now, 1, 2, 3, 4, 5, 6, 7, 8. So 8 goes in here, so 4 minus 0 minus 4 is a formal charge of even better, just 0. That is what we want. Now for oxygen, 6 valence electrons. How many total of non-bonding electrons? 1, 2, 3, 4. These lone pairs are non-bonding. There are 2 pairs, or then 4 non-bonding electrons. Minus 1/2 times the total number of bonding electrons. For oxygen, 1, 2, 3, 4 bonding electrons. 6 minus 4 is 2, then minus 2. That is also the ideal formal charge of just 0. We want formal charges of 0. We want very minimal formal charges. But by minimal, that doesn't mean we want a -3 formal charge. By minimal formal charges, we want neutral formal charges. So the goal is a neutral or a 0 formal charge for each atom in our ideal Lewis dot structures. So some more guidelines here on formal charge and Lewis structures. Number 1, for neutral molecules, a Lewis structure in which there are no formal charges is preferable to one in which a formal charge is present. We'd rather have no formal charges at all. Again, we'd rather have all formal charges of 0 if we can. That is the goal for our Lewis dot structures. Guideline number 2, Lewis structures with large formal charges are less plausible than those with smaller formal charges. 0 is very good, +1 is okay, -1 is okay. We get out into +2 and -2, those are not really okay. Those are not ideal. They can happen in a fairly stable Lewis dot structure, but again, we're going to go for 0 or either -1 or +1 if we have to. Guideline number 3, among Lewis structures having similar distributions of formal charges, the most plausible structure is the one in which negative formal charges are placed on the more electronegative atoms. Electronegativity increases up a group and it increases going left to right. So if we have to have a non-zero formal charge, we are ideally placing a negative formal charge on the more electronegative atoms. More electronegative atoms are stable with electron density around the atom. So if we have to have a non-zero formal charge, we'll go for a negative formal charge on the more electronegative atoms. This can be the trickiest guideline to look at for formal charges and Lewis dot structures. Let's try this practice problem. So a student proposes the following Lewis structure for a carbonate ion, so CO3 2-, a polyatomic anion. We're going to assign formal charge to each atom in this Lewis dot structure. For some additional context on Lewis dot structures and formal charges, we assign formal charges to get a rough idea of how much the arrangement of valence electrons near an atom changes when the atom forms a chemical bond. Generally speaking, the larger the formal charge, the more the arrangement changes. Changing the arrangement of valence electrons costs more energy, so chemical bonds that result in large formal charges like -3, +3, -2 is not ideal either, +2 not ideal. Chemical bonds that result in large formal charges are less likely to form naturally. So with that information, the Lewis structure with the smallest formal charges will usually be the best. Then this trickier but important guideline, if there are several possible structures with the same size of formal charges, it's best to pick the structure in which the negative formal charges are assigned to the most electronegative atoms. So we assign formal charge by looking at the valence electrons in a free atom and then the valence electrons assigned to that atom within a molecule. Do we see bonds around that atom? Do we see electrons that are not in bonds around that atom? This is how we tell the valence electrons assigned to an atom within a molecule. Does it have bonds coming from it or just electrons that are not in bonds? So to assign the valence electrons to an atom in the molecule, we're going to use these rules. Assign all electrons of a lone pair to the atom it's on. Then assign half the electrons of a bonding pair to the atom it's on. All of this is saying this equation here. So the total number of non-bonding electrons, the total number of bonding electrons. But the bonding electrons we multiply through by 1/2. It may be silly, but I'm going to solve this using the thing idea. So for oxygen, it has 6 valence electrons, 6, 6, and for carbon, 4. So we start this out with how many valence electrons each atom has on its own, not yet in a molecule. Then for the central oxygen, it sounds silly, but let's do the thing way. So 1, 2, 3, 4 things around it, that's a +2 formal charge. The right oxygen, 1, 2, 3, 4, 5, 6, formal charge of 0. The bottom oxygen, 1, 2, 3, 4, 5, 6, 7. So that's -1. This is the same thing as looking at the number of valence electrons minus the electrons that are non-bonding minus 1/2 times the number of electrons that are in bonds. This is just another kind of way to visualize it. Then for this carbon, it's 1, 2, 3, 4, 5, 6, 7. This formal charge then is -3. So +2, 0, -1, and -3. This is clearly not an ideal structure, especially for this -3 and +2. We'd rather have much minimal formal charges. We want the formal charge to be 0, not anything greater than that, and not anything less than that. In case you'd rather use the equation that's given, let's try it for carbon. It has 4 valence electrons. It has 1, 2, 3, 4, 5, 6 non-bonding electrons. Minus 1/2 times the number of electrons in bonds. That's 2 here. 4 minus 6 is -2, minus 1. That's -3. We also got -3 doing it this way as well. So be sure you go through all these and definitely make sure you can get the formal charge of +2, 0, -1, and -3. These are the formal charges. It's definitely not an ideal Lewis dot structure because we have a lot of non-zero formal charges. The one thing we should check too is make sure all of our formal charges add up to the charge of a carbonate ion. So 2 and 0 is 2, -1 is +1. +1 minus 3 then is -2. So we do have these formal charges. They do add up to -2. So at least that does work out from this drawing. It's a good thing to check, but given this structure, we would probably want to rework this to more minimize the formal charges. Because we don't have an ideal structure, let's try to figure out the ideal structure. So the first step in drawing the Lewis dot structure is to count the number of valence electrons and figure out which atom goes in the middle. Carbon is more unique than oxygen. Carbon is less electronegative than oxygen as well. So in setting this up, we could draw something like this. Then the number of valence electrons, 4 for carbon, 6 for oxygen. There are 3 of them. 18 plus 4 is 22. Then because of the 2 minus charge, we have 2 additional electrons. That means we have 24 electrons to work with. So far, I've used up 1, 2, 3, 4, 5, 6. Next, we add in lone pairs to the more electronegative atoms, or the atoms on the outside of the molecule. So 1, 2, 3, 4, 5, 6. We're still obeying the octet rule because 6 plus 2 here is 8. Then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We've used up all 18 electrons because 6, 6, and 6. 6 times 3 is also 18. 18 minus 18 is 0 left. But does this carbon have a complete octet? Well, 1, 2, 3, 4, 5, 6, so no. What we can do then is try to move a lone pair of electrons in to form a double bond. What we should do at this point is check that they all have a complete octet. So 1, 2, 3, 4, 5, 6, 7, 8. That central carbon is good. 1, 2, 3, 4, 5, 6, 7, 8. This oxygen is good. Then for these, they're the same. 1, 2, 3, 4, 5, 6, 7, 8. This one's good, so this one is good as well. Now the charge on carbonate is 2-, so do the formal charges of all these atoms total up to 2-. Well, oxygen wants to have 6 valence electrons around it. 1, 2, 3, 4, 5, 6, 7. So this oxygen has a -1 charge. This oxygen looks the same, so it'll also have a -1 charge. 1, 2, 3, 4, 5, 6, 7. It has one more region of electron density around it than it ideally wants to, because oxygen on its own has a valence electron count of 6. We're putting 7 negatively charged areas around it, so it has a -1, an extra negative charge for its formal charge. Carbon has 4 valence electrons. Then it has 1, 2, 3, 4 things around it, so its formal charge is 0. Then let's look at this oxygen. Oxygen has 6 valence electrons. Then in the structure has 1, 2, 3, 4, 5, 6 things around it, so its formal charge is 0. -1 and -1 do total up to -2. Erasing here so the brackets are more clear, and changing the color of this bond. This is a good Lewis dot structure for carbonate. All the formal charges total up to -2. All the atoms have a complete filled octet, and the atoms that have a formal charge on them, the atoms with a negative formal charge, are the more electronegative. They're the more electronegative atoms. Oxygen is more electronegative than carbon, so this structure checks out. Check out example 9.6 for more on formal charge, and definitely go back and try more Lewis dot structure practice. The best way to get comfortable drawing Lewis dot structures is to practice, practice, practice. So try to take any formula, see if you can draw a Lewis dot structure that makes sense for that formula. I'm including one animation here on the formation of magnesium and oxygen coming together, so the reaction that happens. This is a main group element, this is a main group element, an alkaline earth metal that forms +2 ions. Then oxygen will form -2 ions. We know that will be an ionic compound because this is a metal, this is a non-metal. So let me know if you want to work through any practice problems together. I hope you're all doing well, and I will talk to you more next time for more on Chapter 9. I'm also including here some animations that are copyrighted, and they are provided by the publisher.
To demonstration of an ionic and a covalent bond and their differing properties, we have a piece of magnesium ribbon. Magnesium ribbon can be burned in a flame. I'm going to lower it then into this can to protect our eyes so that we don't look directly at the bright white light. The white product formed is the white magnesium oxide. An ionic compound is formed when magnesium reacts with oxygen. It's a very stable compound, as is evidenced by the large amount of heat and light that's released. Here we have a piece of roll sulfur. We can take a small piece of the roll sulfur and place it in the deflagrating spoon. We're going to heat it in the spoon, and the sulfur will melt and ignite. Then we're going to lower it, once it has ignited, into this bottle of oxygen gas so that the flame will be more visible. Sulfur burns with that lavender flame, producing sulfur dioxide gas, SO2. Sulfur dioxide gas is a covalently bonded compound.